So today the topic is developing hardware-in-the-loop tests with AI. Who is PROTOS? We develop software tools, domain-specific languages, test tools, software architecture tools, and also do a lot of consulting for embedded systems. I'm an aerospace engineer actually, but I have a fable for embedded software architectures, tests, and especially domain-specific tools. And I'm PROTOS CEO, so that's about me. So why do we want AI? Let's start with that. Everybody wants AI. So the question is, do we really want AI? And if we want AI, why do we want AI? So let's talk first about some expected outcomes, advantages of development with AI. First of all, you can speed up development for applications and tests. That's I guess that's, well, in some cases a fact, in some cases not. It's not as green as it sounds. It's a big advantage for me. It's easy to refactor existing code. That's definitely something that works in many cases very good. You can generate documentation from code or models, also an advantage. Then you can generate test cases from requirements. Doesn't always work as expected, but you can do that. And you can work without deep knowledge. That's a pro and a con. So if you have no idea what you're doing, then usually the results from AI are equally bad. But for example, for prototyping for something fast, this works really good. For production code, yeah, we have to look at this. Okay, so let's talk briefly about our hardware-in-the-loop approach, because it's not a classical hardware-in-the-loop approach. We are focusing not on the classic tests like the unit test for software components, mainly in an embedded environment, or the big hardware-in-the-loop test or the system tests at the end of development. So what we do is we focus on the integration test, the hardware-software integration test in the early stages, from the early stages throughout the complete project, complete automation for hardware-in-the-loop testing on the desktop of the developer or on a continuous integration server. It's important for you to set up the context that you know what I'm talking actually about. We have a small hardware-in-the-loop test system. It's called Minihill. It's about the size of a piece of paper. I have one on my desktop here for the demo. That's my demo here. We have many industrial companies, also from aerospace, medical, and so on, that use our Minihill to test their software and their integration with the microcontroller. So we test at the pins of this microcontroller the complete functionality of the complete software, unchanged software. So that's to set up the context. Now, back to the slide. One thing or three things you need here in this, let's say in the test system. You need to connect your test system with the actual wires, so with the signals. Let's say digital, analog, SPI, I2C, and so on. That's the first thing you do. The second thing you need to do is to set up a simulation environment, because if you are controlling a motor and the motor is not attached to your system, as an example, your system will fail immediately. You do not even get to the state where software actually works and where you would like to test something, because it fails immediately because there is nothing responding to it. So you need to simulate the environment, the motors, the batteries, all kind of signals, CAN, LIN, and so on. So you need to simulate the environment. And at the end, you can put on top, you can put your test cases. For a hardware-in-the-loop system, usually the environment simulation is the bigger, the more complex part than the test cases themselves. Usually that's, and because it's a bit more complex than doing our unit test, we have our own development environment. It's a model-based environment. to develop simulations and test models. So we generate the code, we run the tests, and so on. So it's a complete cycle here, completely automatable. Now, we want to work on those models. So we want to generate structure for environment simulations, structured behavior for environment simulations, for test cases, and so on. That's what I want to use AI for in this demo. Now let's have a look at which kind of models do you actually need for a hardware-in-the-loop test system. First of all, you want to define test cases. So what we use is a language. We can directly generate sequence diagrams from that to understand what we're doing there. So test sequences is something we would like to model. Also, what we want to model here is state transition testing. That's a formal method or semi-formal method to generate tons of test cases, relevant test cases, very fast from a high-level specification of your expected behavior. So it's a really redundant description of what your system should do. And from there, we generate test cases to prove that it does this or not. So on a very high level of abstraction. So those are typical models for a test case definition. And then you also need to define environment simulations. So there are two kinds of behavior you need to simulate something for. First is state-based and event-based behavior. Here we use state machines for environment simulation, for example, for how a bus system reacts on certain events, or in a machine control, for example, if the end sensor is hit, something happens there and this, and we send a signal back and so on. That's typical event-based behavior, or also for simple motor control systems, could also be a state-based behavior for a motor. And the next model we need, or the other modeling environment we need, is something for data flow modeling, for example, for a motor simulation. So let's say for everything that has a closed loop or needs a closed loop simulation, closed loop control, like a motor, like a battery, and so on. And at the other end, you also need to simulate the system. So usually there are tools used like Simulink and so on. We also have some modeling integrated you can use to do that. So those are the models we want to produce with AI. We're using in the core of our test and architectural systems and so on, we use the method ROOM, real-time object-oriented modeling. It's been designed for complex embedded systems, and essentially a hardware-in-the-loop system is a complex embedded system, or in some cases also a simple embedded system. We put the architecture in the center of development, and it enables many other tools and methods, and so on and so on. So if you are interested in the method, I can send you a PDF version of our book, please, or download link. Please send me an email if you want to have access to this book. You can also order it at Amazon and so on. So, but it's just to inform you that there is a method behind this. Now, in the core of this method, we have a textual language and textual languages are really good for LLMs and for AI. You also can use an XML file or whatever as an input, or as an output, actually, what you want to generate. But AI can interact very good with textual languages. For example, translating a text from German to English or something like that. So you do not need any specific interface for AI for textual formats. So the textual format is sufficient usually. But the advantage, for example, in comparison to something like XML or other machine-readable languages, is that you can version control it, branch it, merge it, do pull requests. So you do not need any specific tools for example, for diffing the two versions, so the previous version and then the additional AI-generated version or input from your models, because you just need a text editor to diff and merge, so like something like a Git or a WinMerge or whatever you're using. So you do not need any specific tooling. That makes life easier because you need to verify what the AI actually generated here. Then, so that's the next point here. You as a human being can directly see what the AI, what the changes in your code base made by the AI is. You do not need any additional model editor or whatever or model differ to see that. And also one important thing is the examples and descriptions for AI are easy to develop as a textual input. I'll show you this later in my example. So those are, from my point of view, big advantages of textual languages in comparison to, or human readable textual languages in comparison to something like XML, XMI, or other binary languages or whatever. So the AI actually doesn't care which kind of language this is, but you as a human being need to verify what the AI did. So next step. Now I've made the case for textual languages. In our infrastructure for this for this room tooling, we're using also done by us open source project. It's called eTrice, and it's an implementation of the language real-time object-oriented modeling. And the two main things you can do with it, you can design structural architectures, hierarchical structural architectures for complex systems in a very simple way by defining actor classes, and you can drill down and refine the models hierarchically with layering or with containment hierarchies, very powerful for modeling hierarchical embedded systems. And the main model is a textual modeling language here, but you also can interpret the model as a graphical model, either view it or edit it as a graphical model, but you always diff, merge, and version things and do pull requests and so on the textual model. That's very important because that's where we have a closer look at it. So that's the structure of the models. We also can design behavior, as an example, a state machine, also data flow models and the like, or other things. And the state machine is a typical example for event-driven modeling approach. And this is also designed as a textual model. You can imagine you can diff and merge such a state machine very easily on textual level. You do not need any graphical editors to do that or viewers, but you can edit and view the state machine also on a graphical level. So it's just two editors that work on the same model, two concrete syntaxes, if you will. Now, the third editor I want to show you is the test case modeling. So there's again a textual language that's interpreted as a graphical sequence diagram. So for example, you define a sequence, a test sequence, test steps, and so on with hardware interaction, IO interaction, or interaction with simulation elements and so on. And out of those sequences, you get a generated view, flat world view of a sequence diagram that shows you exactly the complete context of all the steps. That's important to discuss things in a team, to interpret what you did or what the AI generator did on a high level of abstraction. Very important, because you want to know what it did before you rely on the generated test cases. So textual languages, that's the big advantage we have here with this method. Now, the tooling, as tooling, we are currently migrating, or we already migrated from Eclipse to Visual Studio Code with all our editors, viewers, and so on. So currently it's only missing one or two little features there, but I'm going to show you this tooling in a minute. We use Visual Studio Code also for the AI demo because it integrates really nice with the GitLab Copilot. Yeah, GitLab Copilot. No, GitHub Copilot. I have to change the slide here. Sorry, my bad. It's a GitHub Copilot, and with the Git process, and so on and so on. And we have migrated the Mini Hill Development Studio to Visual Studio Code plugins. all the textual languages for structure, behavior, test cases I've shown you before, they're all in there. And we also have graphical editors and viewers. One viewer is still missing, but that's to be made soon. So it's already a production environment here. Now here on the sidebar, you can see the chat of the GitHub Copilot. And I'm going to show you this. Now, our results with the pilot customers and projects. So it's in production for, let's say, smaller first projects, first with friendly customers. So AI is very efficient for generating simulation and tests for smaller, very specific tasks. The more specific, the better the results. I guess that holds in general for AI-generated codes. Then one use case we found very helpful is to train new test developers. So instead of reading documentation, and you never find the right place in the documentation, depending on what you're looking for, you can generate specific examples or productive code to learn how it's done. That's a very powerful use case, especially for new developers. Then you can generate structure models. So for example, environment simulation, you need structure models. This works really good because usually in Room, for example, the structure models are relatively simple. So they are very powerful because they are very simple. So Room is reduced to the max, especially for structure models. So the AI gets the structure models really, really good and really right. Then you also can generate simple environment simulations like state machines, data flow models for closed loop simulations, for example, but simple. So more complex things are more complex. And I mean, AI is not intelligent. So we never forget that. It's not intelligent. It's a very productive aggregation machinery and filter and so on, but it's not in our sense like a human being intelligent. So it does not know really what it's doing. You can refactor models. That's a very productive use case, especially structural models. You can not only generate, but also refactor very good because it's easy to get the syntax right here. And it's something you might need a lot of time for. That's something the AI can really speed up immensely. Then you can generate test cases from a test description or from requirements. Works for now, in our experience, better from a specific test description. But also, yeah, we also have success with requirement-based generation. Yeah, the more specific, the better, let's say. So it can speed up the work if it's done right. Now let's have a look at what that means. I'm going to give you a little demo with our tooling. And I've prepared a larger demo, but I won't run this live because, yeah, that's also a problem with AI. In many cases, it's not really deterministic and repeatable. Yeah, that's the nature of AI. It's statistically. So, for example, for the demo I'm going to show you, I pre-generated the demo because if I redo it, it always gives you a little bit different examples. In some cases, it doesn't get the syntax right and things like that. So we're still working on that part. But in a second demo, I'm going to show you for a simple test case what it looks like, and I'm going to try to run this. So please forgive me, it doesn't run. If it doesn't run, it's really a live demo, and I do it the first time with this example. So we'll see what happens. So no risk, no fun. That's my motto here. So let's jump in the Visual Studio Code environment. As I said, I have on my desktop this little test system. We will run this later on. And now I'm going to show you how did we explain to the AI, because there are not many Room examples on the internet. Actually, there are, but not so many like let's say trading with Python. You can generate a complete trading bot with an AI for Python, because there are hundreds of thousands of examples of code out there. So this will be very efficient. But then you're the 101st,000th example out there. So what did we do? We created room language syntax files, examples on grammar level. So really the abstract syntax tree or the grammar for the language. Then concrete file examples for the language, annotated with documentation. That's something you can see here. So those are valid examples for room files. And so we have many more examples, of course, there, and specific Copilot instructions for the let's say for what do we expect, what patterns it should use, what to do with hierarchies and things like that. So it's more what kind of architecture do we expect from the AI here. Now let's have a look at a typical example. I show you that's the prompt here. I told it to create a new room file for a motor control system in the folder AI demo. So that's the prompt. I'm going to show you a couple of other prompts I'm using. So that would be the one I used in this example. But you get much better results if you're more specific. So those are a couple of lines more that produce a better result. But you need, for a real production system, you need much more details than that. But in addition, we provide all those examples with more generic instructions for the AI. So the prompt is more complex than just this line here. So I've used this simple approach here, and later I'm going to use this for test case generation. So it generated the file, so that's the output. It explains what it does and so on. And then, thanks to the infrastructure at Visual Studio Code, the AI has access to the editors. You see here the syntax highlighting, for example, and so on. So let's open the generated file. It's clean, but it has not been clean in the first run. So it had four syntax errors, and in many cases AI corrects the Copilot corrects the syntax error immediately, but in this case it failed. So I told it explicitly to repair the syntax errors, and it has detected several syntax errors. 4 syntax errors. That was exactly what happened here. Then there has been a problem with the network connection to the server here. I tried it again, and in the end, I got a syntactically correct room model. So that's the textual model I created, and the textual model also contains so 2 state machines, for example, and a system here. So let's have a look at the structure in a text editor or a text viewer. So that's exactly, for example, the structure for this here. Then that's another structure. I also have hierarchies in there and so on. So let's have a look at the generated behavior. So it created several components, including some state machines. So also a state machine, for example, a hierarchical state machine in this case. So that's the hierarchy of the state machine. So it generated a state machine that tries to implement a PWM-based motor controller. So I did not provide any specific information about that, so it's a very generic approach here. It's syntactically correct, it compiles and so on, but that's not what I would have done, and it also does not work correctly, but mostly because I did not give more specific information. So that's what is generated. So that's the complete file here. You can imagine if you know exactly what to do and just want to be faster and speed up the process, this can help immensely. But if it gets more complex, you need to put a lot of time into reviewing the results, repairing things that are different than you expected, or refining the prompt. So in some cases, it takes longer to refine the prompt or to repair the results than to if in comparison to if you would have done it manually. So that's a bit more complex structure and behavior for example, for an environment simulation. And now I'm going to do a little example for a motor control test case. So I have, let's have a look here. I have some test steps and some test sequences. I'm briefly switching to Eclipse because that's the same file, by the way, really the same file. And here you can see what is generated from this textual language. We generate sequence diagrams. That's the only viewer we have not migrated yet to Visual Studio Code. So, but that's the same file. Now let's give it the context of this file. So here I'm in the context in the Copilot chat. I'm in the context of the cage file, and now I'm going to grab a little example from my demo prompts that would be a bit more generic, and here I'm a bit more specific. Let's take this bit more specific example, and I'm going to switch the context back to this file. So now I'm in this file again, and I'm going to use this to add a test sequence to the existing file, motor controller.cage and so on, with a loop test to test the speeds from 0 to 10 in increments of 10. That's relatively specific, and let's have a look at what the system actually, what the Copilot actually does. Now it's analyzing this file and all the files I predefined as an input, like also a cage, so the language file for those test case specifications. Now it generates something. Let's see what happens. Now it added the code for the test speed range full sweep. It invented this here, but it didn't. I suppose it did not add this to the test test suite. So here there is, in the test suite, there is no reference to this file here. So let's add this. That's something it forgot because I have not been specific about this. Let's add this to the motor integration test here. Now I added the generated test case to my test test suite. So that's the generated test case. I keep it for now. It should be syntactically correct. Now I'm going to change the editor context just because of the viewer to my old Eclipse environment here. And here you can see that's the generated test sequence. And here in this generated test sequence, I see what it does. It makes a loop for set and check and includes the set and check speed. It found the pre-implemented set and check speed, which does exactly what it says, and it added a loop. This would be a nice example for somebody who is learning this language, how to create a test sequence or how to create a test step that expects a certain result or something like that. That's very specific. So now that's the generated test case now, and I'm going to revert. Let's only commit the generated file. So that's what has been generated. It's only this part here and this part. So that's the AI generated part. Now you can see why it's good to have a textual editor. That's something you can interpret very nicely and review very nicely as a human being. So now I'm going to AI test case, going to commit this to my Git repository locally here, and the continuous integration server in the background. It already, or it detects very fast by a commit hook that it has something to do. And now it's going to check out the new version of the AI generated test case now of the diff. It assembles the project, and then you will see that it flashes the project directly to the hardware in the loop system here, or microcontroller in the loop, processor in the loop. There are different names for it. So it assembled the project. Now it should start to flash it. Here you see the LED stopped. Now it has resetted the system because it has been flashed. Now it's flashing the system under test. There was nothing to do because I did only change the test case, and now it's running the test. So now the motor simulation works, the test cases are running, including the newly generated test cases. So now let's have a look at how the hardware loop system runs. Yeah, that's a text log just to see what happened. And now I can see there has been a problem because it's yellow. So yellow means a test case failed, and it's really the test speed range full sweep. That's exactly the test cases the AI generated. That's okay, because maybe it found some bug, maybe it has a bug. So let's have a look at the demo integration test here. So here you see that's the log. That's not the specification, but that's actually the log from the test execution. It has an error, and here it could not. So that's the full sweep. It activated the motor control, it set the temperature, and then it set the speed to 10. And I would have to analyze this now. I suppose it got the expected result values wrong. So it should be between minus 500 RPM and 500 RPM. And I suppose that has been wrong. So how could I change this? I could create a very specific function. That's what I should have done in the first place, to set the RPM to a certain value, and the value needs to be transformed into the let's say the hardware specific units I'm using here in this example. So that's the part it did not get right. It did not understand really how the calibration of the model works. So just as an example, now that's what I wanted to show you. Let's wrap this up. I have some things you should probably not do or be aware of. So artificial intelligence is not intelligent, but it's a brilliant idiot. It's not by me, but I quoted this because I think that's exactly what it is at the moment. It's very fast in aggregation, filtering, and altering of data. So if you use it that way, you can be really fast. Another problem, especially for more complex problems, is that the context window is very small. If you give it a very big context window, usually this doesn't work, or you run out of computing power or space or whatever. So only small models can be in the context, at least with an affordable budget. So that's a problem for more complex situations. Then another topic is the statistical nature of AI. It doesn't give you deterministic results. You always need to verify what it actually did. As well, if you do a prototype for something, that you get away with it, but you usually do not exactly. It does not exactly what you expect, or what you would do as a human being. That's okay if it gets it right, but this missing deterministic is really a problem with safety critical system, with robust systems that are extremely expensive if they fail, but especially if life are at stake, that's not what you want. Then you have so as a result, the results of bigger and more complex tasks, they need to be reviewed and corrected by human developers. And in many cases, this reduces productivity. In some cases, to the point where you actually would have been much faster if you would have done it manually. And for me as an architect, so I'm a big fan of reusable architecture, things like decoupling, cohesion, modularity, and so on. AI usage leads to a lot of copy and paste. So it leads to much less reusability, and in the end to not very good architectures. So very often you have a system after that gives you less quality and less maintainability, also less flexibility in changing things, and so on. And more generic, garbage in, garbage out. You need to be very specific and precise with your prompts. If not, you cannot really use the result. So what are our next steps regarding AI? We want to, with our system, we finalized the Visual Studio Code integration for the mini-hill tools. We fill the gaps for the language support. So there are still, for example, for the hierarchical state machines, we need to provide more examples because it doesn't really get it right, or it takes decisions I wouldn't have taken as a human developer. Then, yeah, we want to make a first release of the AI support to our customers. We already have some customers working with this. We want to find out which information can be defined in a generic and reusable way, so as much as possible. So, for example, those language definition files and so on, not every customer or not every user should do them, need to do them on his own. And we want to generate test cases directly from requirements. So, of course, if you have a requirement like as fast as possible, that's impossible to generate a test case from it. So also the requirements need to be very specific in order to generate test cases from them, but it works in some cases really good. And we want some predefined stable use cases and prompts with the biggest benefits for you. Now, that's it from my side. So thanks for your attention.